The Doppler effect is a very important phenomenon of sound waves. Pretty much it's so useful because it lets you figure out how fast something is moving by the waves that it gives off. And let me give first an example from astronomy. Astronomers can figure out that a star is wobbling by looking at how its spectrum shifts. Now, in this case, it's electromagnetic waves, light that's coming off the star, but the effect is similar. The spectrum of the star wobbles as the star is wobbling, and it tells the astronomers, hey, there's a planet orbiting the star that's producing that wobbling. Now, let me show you some more down to earth examples of Doppler effect that you've, I'm sure, heard before.
Ch17 working him. Right. Back in the
Why does the Doppler effect happen? Here's a source of waves at rest. Spherical ripples being sent out from a source, like a train whistle. If the source is moving, the source of the sound waves is in motion, then the pattern of the waves gets distorted. Here's a moving source of sound waves, and notice how the moving train, it's catching up with the waves it emitted in front of it. It's running away from the waves emitted behind it. That leads to a compression of the waves in front and a stretching of the sound waves behind. The waves off to the side are also distorted as well, unless you're at 90 degrees from that line. But we're going to only derive a formula for the Doppler effect along the line of motion. Okay, so let's work out in detail the calculation. So here is our source of sound. So if it just stayed at rest, it would be emitting waves every time period t. And so time period t in the past, it emitted a wave. I'm just going to draw their waves moving to the right. And so if it were just at rest, if this were just the sound source at rest, this distance would just be equal to the normal wavelength of sound, lambda, which is equal to the speed of the sound waves, which I'm calling v. I'm not going to call it vs for reasons because I want to call vs the speed of the source. So it's going to be the speed of sound multiplied by the period. That would be the normal wavelength, the distance between the wave it emitted before and the very next peak of the wave that comes out. Now, if the source of the waves is in motion, this is S, the source. If the source is in motion, then the next wave that comes out is not emitted from that point, right? If the source is actually in motion, then the next wave that comes out is going to be when the source has moved over here. That's the source moved slightly to the right. And if the source is in motion, well, then we know what that distance would be. That distance would be Vs, the speed of the source, multiplied by the period of the sound waves. At that moment, that's when the source emits the next sound wave, when it's right here. And you can see the effect. The effect is now there's a shortened wavelength, shorter than the original lambda. There's a new wavelength, lambda prime, smaller. How much smaller? Well, it's just the original wavelength, lambda, minus however far the source advanced in one period of the sound, minus VST, which can be simplified. The original wavelength is just V, the speed of sound, multiplied by the period. So this is V minus Vs multiplied by the period. And that is at the crux of it here. The moving source distorts the wavelength of the sound. and here's the distortion of the wavelength that occurs. Notice that if the source were moving to the left, in other words, if I'm over here and I'm listening for those incoming waves, if the source is moving towards me, I would pick up this shortened wavelength. However, if the source were moving away from me, the wavelengths are lengthened, and I would have to change the minus sign to a plus sign. It would be a lengthening of the wavelength instead. Okay, so this is at the crux of the shift in the wavelength, but let's write down the equation for the shift in the frequency, f prime. What's the frequency in the sound that this person is going to hear? Well, to figure it out, you take v, the speed of sound, divided by the wavelength. Speed over the wavelength will tell me how often the waves arrive at me, listening over here. Okay, so this gives me, remember, v is the speed of sound, vs is the speed of the source. So I take v divided by lambda prime, and that gives me v minus vs. I have 1 over the period, which is just the original frequency. And so that lets me predict what frequency I would hear as the observer. I have to divide v over v minus vs. That's the Doppler shift factor. Okay. Now this equation as written is only accurate when the observer is at rest. Source is moving, but I'm not. Can we generalize it to account for any motion that I might have? Like, for example, what if I am running in to, the incoming waves? What if I'm running to the left in this figure? Well, there's still the lambda prime effect, the shift in the wavelength. But if I run into the waves, then isn't the effect as if, for me, the speed of sound is greater? Like I'm running into the waves coming at me. Then to me, it looks like they're coming in faster. It looks to me as if they're not coming in at speed v, but a sort of boosted speed, v plus my speed. So we can then have a more general equation that accounts for both the motion of the source and any possible motion of the observer. Like the star is moving, but the Earth is also in motion. So there's a sort of combined effect, a combined Doppler effect. So I would have to replace v with v plus v observer. I'm the observer, letter O. And I have to divide that by that lambda prime, which we saw gives me v minus vs multiplied by the original frequency. And that is the Doppler effect. It's the frequency heard by the observer when the source and the observer are in motion. Notice carefully the signs that are used. We have to be extremely careful when using this equation to possibly adjust the signs in the equation, the plus or minus signs. For example, V plus VO. Well, that's appropriate if I'm running towards the sound waves. However, if I'm running away from them, then I would have to replace I'd have to replace the plus with a minus sign. Likewise, the shift in wavelength, if the source is heading in my direction, shortens the wavelength, and we had V minus Vs. However, if the source is moving away from me, then I have to replace replace it with V plus Vs. So I'll do a number of examples where we have to, switch the sign depending on the exact circumstances that are present. Now, some examples which illustrate how you have to be really careful with the signs to use the Doppler effect equation. We've got two submarines. First, they're approaching each other. Then they pass and they recede away from each other. In this case, it's sound waves in water. They don't move at 343. They move much faster. Sound moves much faster in water. So first, they're approaching each other. Here's submarine A sending out sound waves, and it's moving, let's say, to the right. Submarine B is heading towards it. A moves at 8 meters per second, B moves at 9. So I'll first calculate the frequency heard by sub B. Okay, in the numerator, this involves the speed of sound that the observer would measure. Sub B is heading into the sound waves, so it's going to pick up a boosted speed of sound. I would plug in 1533 plus 9 in the numerator. Now, sub A is moving to the right, and B is listening in front. So B is going to pick up the shortened wavelengths. So therefore, you're going to have 1533 minus 8. Just like the equation shows, I didn't have to change anything in that case. You multiply that by the source frequency, which is 1400 hertz. And it gives a frequency which is 1416 hertz. In the next case, A and B have passed each other. So now B is headed off to the left. That's B, and A is continuing on to the right. Still emitting the sound. But now submarine B is behind A, and so it's picking up the longer waves that are on the backside of sub A. So now we got to be very careful about the signs. Submarine B is heading away from these waves. Therefore, the effective speed of sound is reduced. So now in the numerator, I would have 1533 minus 9. Notice how I had to change the sign. The denominator has to do with the wavelength. And the wavelengths are lengthened. So I would have 1533 plus 8. For this case, I multiply that Doppler factor by 1400 hertz. And that gives me a lower frequency, which comes out to be 1385 hertz. Helpful to just do a quick sketch so you make sure you're accounting for the speed of sound, effective speed of sound, and the wavelength effects correctly. Here's an ambulance. Siren is 450 hertz. A car is moving in the same direction at 25 meters per second. What frequency does the person in the car hear as the ambulance approaches and then as the ambulance passes the car? So again, two cases. So first, here's the ambulance. It's approaching the car at 42 meters per second. The car is moving in the same direction, but at a lower speed, only 25 meters per second. So the ambulance sending out its sound waves, they're going to be bunched up on this side because of the Doppler effect. So I'll figure out F prime. Again, back to the general formula. You do V plus V observer over V minus VS. Observer, source. Okay, the numerator has to do with the effect of speed of sound. In this case, the car is heading away from those waves. So I would have to take 343. It's sound waves now. I'm assuming they're going at 343 minus 25. It's as if the sound waves move slower according to the car. What about the waves? The waves are bunched up, smaller wavelengths. So I would need 343 minus 42. Notice how I had to change, signs in the depending on the circumstance. I multiply that by 450 hertz, and I get a value of f prime, which comes out to be 475 hertz. The ambulance is approaching, and so there is an upward shift in the frequency, even though the car is moving away from it. It's not moving away as fast. Notice if they are both moving at the same speed, the numerator denominator would cancel, and you actually hear no shift. The wavelengths are shorter, but you're moving away, and they balance out. Okay, now after the ambulance passes, now the car is behind it, and the ambulance is moving off to the right. They're both moving to the right still. It's just now that the ambulance is in front, and so the waves, you're getting the longer waves on this side. So let's figure F prime. The speed of sound effect, now the car is moving into those waves. And so you'd have 343 plus the speed of the car. The wavelengths are lengthened on this side, so I would have 343 plus 42. That's the Doppler factor multiplied by 450 hertz. And that gives me a lower frequency, 430 hertz. Okay. Bats use a form of sonar. They chirp and they listen for the reflected chirp that comes off like a bug, and they can use that to figure out how the bug is moving, just like submarines use sonar. Let's sketch out the situation. We have our bat. It's chasing an insect. It's just that the speed of the insect is unknown. I'll call it U. The bat has a known speed, 5 meters per second. The bat emits the chirp. Now it's moving when it's emitting the sound, so there's a shift. Then the sound reflects off the insect, and the bat picks up the echo, call it echolocation. What you have to be super careful about is that in the reflection, there is an additional Doppler shift. Okay, so you see the insect would be hit by waves of frequency f prime. But those waves then reflect off the insect. The insect is in motion as the waves are being emitted from it, and so there's an additional Doppler shift there. There's an f double prime that has to be accounted for. That's the frequency the bat picks up in the reflection. So these kind of problems are very important. Any kind of echolocation or sonar type problem, anytime sound is reflecting off of some object, it is always a double Doppler effect. Any kind of exam question is going to involve a double Doppler effect, where there's some kind of echo in the sound. Okay, so let's spell it out and see how it works. So first, there's the sound which actually hits the insect. That's F prime. The insect is moving. In this case, the insect is the observer of the sound. It's getting hit by the sound waves. So I would have to use the speed of sound minus u, minus because the insect's heading away from the sound waves, v minus u. The sound waves themselves are shortened in wavelength, so I would have v minus 5 from the bat's speed, and I'd multiply that Doppler factor by the 40 kilohertz frequency. F prime is not the frequency that comes off the insect, and it's not the frequency the bat's going to hear. You see, the frequency that the bat is going to hear is really shifted again. I would have to, so now these sound waves are coming towards the bat. That would be V plus 5. Now the bat is the observer of these waves. So V plus V observer. These sound waves are being stretched out because the insect's moving to the right while the bat's behind it. So you'd have longer wavelength, V plus U, in the denominator. The insect picks up frequency f prime, and that's the frequency that gets shifted again by the motion of the bat and the insect. So, in other words, f double prime is really, it's a double Doppler because there are two Doppler factors. I have to plug in this f prime right here to get the full expression for the Doppler shift. So it's v plus 5 over v plus u. That's the shift on the way back to the bat, multiplied by the shift on the way into the insect, which is v minus u over v minus 5. It's that double Doppler factor times the original frequency that the bat will hear. So in this problem, we are given the emitted frequency from the bat, 40 kilohertz, and what frequency it hears on the way back, which is 40.4. So in other words, we're given that f is 40 kilohertz, and we're given f prime is 40.4 kilohertz. So you would plug in for f double prime and f, and it's now an algebra problem to solve for u. The speed comes out to be a speed of 3.3 meters per second. So the bat's brain can interpret f double prime and figure that the insect's moving at a speed less than the bat. Bat's moving at 5, and the insect's moving at 3.3. So the bat's going to catch up and catch the insect. So there's algebra involved in solving for u. I highly recommend that you familiarize yourself with your calculator. I think you have a graphing calculator. And your graphing calculator, it won't do the algebra for you, but what you do is you plot two functions, y1 and y2. y1 is just equal to the number of 40.4. y2 is equal to this whole function of u on the right-hand side. You look for the intercept of the two graphs, and your calculator will tell you the intercept, which is the solution. So you can bypass doing algebra on an exam by being familiar with using your graphing calculator. Here's another double Doppler or sonar type problem. We have a ship at rest in the water. The ship is at rest, but it sends out sound waves in the water which reflect off a whale. And want to figure out the frequency that gets reflected back. So first question is, what's the wavelength of the waves emitted by the source? Well, since the source isn't moving, the lambda prime is just equal to the normal wavelength, which is just v over f. That's just the speed of sound in the water divided by the frequency. There's no shift because the source isn't moving. Okay, question B, the difference in frequency between the directly radiated waves and the waves that reflect back from the whale. This is where we have to use the double Doppler phenomenon. So first the waves come off the ship. There's the ship and the whale. The waves come off the ship. The whale is moving at 4.95 meters per second. Okay, so this is f prime. F prime, it's v plus v observer divided by v minus vs. It'll be v plus 4.95. V is the speed of sound in the water, which is over 1,400 meters per second. I have to divide by v minus vs, but the source isn't moving, the ship isn't moving, so it's dividing by v. That multiplied by 22 kilohertz. Gives me a frequency which is equal to 22.07. Okay, that's the first Doppler shift. That's the frequency that the whale hears. The whale now emits that frequency, but it's emitting it while it's in motion, so there's that secondary Doppler shift. Now the ship is the observer. The whale is now the source of waves f prime, and it's emitting that f prime while it's in motion. So the ship now picks up f double prime, v plus v observer. Now the observer is the ship on the second part, so it's v. Ship's not moving, and then the waves are shortened by the motion of the whale. So I have v minus 4.95. It's that times f prime times 22.07 kilohertz. Gives me the double shift to be a frequency of 22.15 kilohertz. So the ship emits 22 kilohertz. The difference between the original frequency and the double shifted frequency is 0.15 kilohertz, or in other words, 150 hertz. Much lower range. And so actually how sonar works is it just listens for the shift in the frequency. There's a thing called the beat frequency, which you learned about. We'll talk about it again in a later chapter. But you just listen for the beat frequency between the two, which is measurable, small enough to measure it easily. And then you can figure out the speed of the whale from that. In this case, we were given the speed of the whale, but in practical application, you figure out the speed of the enemy sub or whatever based upon the double Doppler shift.